Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Now we are going to solve problem 5.59, which is a throttling valve. Here we have a refrigerant R341A being throttled in a throttling valve. At the inlet, the refrigerant is in a saturated liquid state with a pressure of 700 kilopascal. At the exit, the pressure drops to 160 kilopascal. We need to determine the temperature drop of this process, which is equivalent to the change in temperature, which is delta T equals to T2 minus T1, right? We also need to determine the final specific volume, which is small v2. First, let's look at the conservation of energy, which is the first law of thermodynamics for throttling valve. We have rate of energy coming into your system minus rate of energy transfer out of your system should be equal to the rate of change in the energy, which involves internal energy, kinetic energy, potential energy. And because this is a steady flow, this part of the equation, or the rate of energy, becomes 0. One thing to remember about throttling valve is it is a small device, and because of that, there isn't much time and only small area is available for any effective heat transfer to occur. So we take a throttling valve as an adiabatic system. So when we expand this part of equation, we have the rate of heat. This is the standard expansion. And the rate of work, and also the rate of energy from the mass coming in and out of your system. Should be and rate of energy from the mass. Okay, 0. Now, since just now we say that we consider a throttling valve as an adiabatic system, this one goes to 0, and there is no work interaction. This part also goes to 0. So what's left from the equation is just the rate of energy transfer that involves the mass coming in and out of your system. So let's expand this part. When we expand, it becomes the mass flow rate coming into your system multiplied by the flow energy, the internal energy, kinetic energy, and potential energy. It's the same on the exit. Flow energy, internal energy, kinetic energy, and potential energy. Now, the potential energy can be considered as negligible, so does the kinetic energy. So now, what about your mass flow rate? You need to remember that for a steady flow system, the conservation of mass principle says that summation of mass coming into your system is equal to the summation of mass going out of your system. So in this problem, you only have one inlet and one exit, right? So the mass coming in should come from point 1, and the mass coming out should come from point 2. So the mass flow rate is the same. What happened in this equation is that you can it cancels each other. So what's left from your equation is only the flow energy and the internal energy. So what it says here is that the summation of flow energy and internal energy at the inlet is equal to the summation of flow energy and internal energy at the exit. And you can simplify this further because you notice that this is actually your enthalpy. So this is the energy balance equation for your throttling valve. Now let's look at the initial condition and the final condition of our throttling valve. We know that from the question that our P1 is 700 kilopascal and it is a saturated liquid. So since we have a pressure, what we do is we look at pressure table for refrigerant, which is table A12. Okay, and I have here table A12 with me. So let's look at 700. So we can see that the temperature is 26.69 and also the saturated liquid, the enthalpy of a saturated liquid is 88.82. So we take these two values and we put it here. Eighty-eight 0.82 joule per kg. Now, let's move to the final condition. We know that our P2 is 100 kilopascal, 160 kilopascal, and then we know that our enthalpy at the exit is equal to the enthalpy at the inlet, which is 88.82 kilojoule per kg. So now, let's again look at table A12 because we have the pressure. Okay. What we should do now is that we should get a value of our enthalpy and also the saturated liquid enthalpy and the saturated vapor enthalpy. So when we look at 160, we see that this is our HF and this is our HG. So this is equals to 31.21 kilojoule per kg. This is equals to 241.11 kilojoule per kg. So what we do now is that we compare these two values with our actual H2 because we need to determine what is the state of our final condition. So when we compare this value with these two values, what we can see is that our HF is less than H2 and H2 is less than HG. So from here, we can say that what we have at the exit is a saturated mixture. Okay? Since we have a saturated mixture, it means that the temperature at the exit is equal to the saturation temperature. And then the saturation temperature at that particular pressure is minus 15.60. Now that we have both temperature, we can find the temperature drop, which is delta T equals to T2 minus T1, and this is equal to minus 15.60 minus 26.65 degrees Celsius, and this is equals to minus 42.3 degrees Celsius. So you have answered the first part of the question. Next, we need to determine V2. From the quality equation, we know that the average specific volume is equals to VF plus XVFG. So now, first we need to determine what is our X. And since we have the enthalpy value for the exit, we can get X from this equation. H2 minus HF over HFG. So we will refer to table A12 at that value. We already have this value earlier on. Okay, so we get HFG, and HFG here is You can either get it straight away from table A12, like this one, yeah, or you can also get it from, there are two ways, direct from table, or is actually Hg minus Hf, and this will give you the value 0.274. Okay, next you use that value to get your V2. So V2 is equal to Vf, you get that value from table 812, 0.7435 plus your x, 0.274 multiply with 1.2355 minus 0.0007435 equals to 0.0345 meter cube per kilogram. Okay, thank you.